Right, morning everybody. Hope everyone's had a lovely Easter. Hope everyone is raring to finish some A-level maths. How is everybody? Oh, okay, just make sure that everything is adjusted nicely. Okay, right. So the last part of mechanics is to do with more kinematics, which remember when we looked at kinematics before, we were thinking about Suvat equations. We go okay, but we're fed up with lockdown. Yeah, I can totally understand that. I would rather like lockdown to finish now. But hey, we've got to do what we've got to do. I'm fine, thank you. Everyone, hope is fine as well. So the plan today is to see how vectors can potentially affect how Suvat works, if it affects how it works at all, and think about, can we get used to having vectors in our Suvat equations rather than just scalars, rather than just having a number for a velocity. We could have a vector as a velocity, so that way we can get to describe things in 2 dimensions in one go. Okay. So, we're going to do most of that, and hopefully this unit should be relatively short. Okay, so we're going to look at vectors equations of motion, which is what we're going to do now. We're going to look at variable acceleration, okay, and we looked at variable acceleration a little bit in year 1, I believe, and we're going to be thinking about finding the velocity given a position, or finding the acceleration given a velocity, or something like that. We're going to be thinking about Newton's laws again, kind of building up on all of the things that we've done so far. And then we're going to be looking at integration with those same vectors of motion, okay? So remember that integration is all about finding distances, finding areas under graphs. So that will come into what we're going to do with Suvat and vectors there as well, okay? So let's first try and get a little bit of a grasp of what vector motion actually is, what it looks like, what it represents, okay? So let's say that we have a vector, okay? And the vector represents the position 3, 1, okay? So that means that with respect to an origin point, which may or may not be useful, we start at a position 3, 1. With each second, this ball moves 4, 2. Okay, and that essentially represents the velocity, because it's saying it moves 4, 2 each second. Velocity is a measure of meters per second. Okay, so if we have this, where would it be after 1 second? Well, after 1 second, it will have moved 4, 2 on top of 3, 1. Okay, so it will have moved to 7, 3. Okay, the top will have increased by 4 after 1 second, and the bottom will have increased by 2 after 1 second, because it's travelled 4.2 meters per second. After 2 seconds, it will have travelled another 4.2. Okay, so it will have travelled up to 11.5. Okay, so we can get a sense of where something will be after a general time t. Okay, so we could say, like, after 3 seconds, it would be 3, 1 plus 3 lots of our velocity. Okay. If it was after 10 seconds, we would take our original starting position and do 10 lots of our velocity. Okay. And that essentially kind of gives us this nice little thing here is our starting point, which is 3, 1, and then t lots of our velocity, which we could rewrite as a different vector here. Okay. Now, if you would have done further maths, you may recognize this as to do with vector equations of straight lines. Okay. And if we were to kind of take this and simplify it, rather than thinking about vectors, thinking about just numbers, what we have said is the distance that it travels is equal to its velocity times time. Okay, which is just a rearrangement of speed equals distance over time. Okay, so we've said that position equals velocity times time. Okay. And if we have some kind of starting position, we just add that on top. Okay. Rather than distance equals speed times time. Okay. This is essentially thinking about the vector form. This is essentially thinking about the scalar form. Okay, we're going to be thinking more about vectors. Okay. So how do we start using this and SUVAT? Okay. So most of the context of the problems will remain relatively similar to what we've seen before. We're going to have things moving with constant velocity, starting at a position and starting at a t equals 0 or something like that. All of those kinds of things are going to be very similar. We're just going to have to look to establish what are our speeds, what are our velocities, not speeds, what are our velocities, what's our acceleration, and bearing in mind that if we're using vectors, we may have it in either ij form or we might have it in column notation. My personal thing is I don't like the ij notation. I prefer things in column form, but both could, in theory, be used. Okay. So when we're thinking about SUVAT equations, there's some conventions that we need to think about. One of which is that we use r instead of s for displacement, and that's because of to do with position vectors. Okay, in further maths, we think about position of a vector being an r vector. Okay, it's the normal notation that we would use. Some things will be vectors, some things will be scalars. Okay, we've already established that r, our position, is going to be a vector. U, which is in one dimension, is thinking about our speed. We can have speed in 2 dimensions, and then it would then give us some kind of direction. It would be a velocity. Okay, so our u can be a vector. Well, if u is a vector, that means that v has to be a vector. Okay, because u is a starting velocity and v is a finishing velocity. A, our acceleration, will also have to be a vector. Okay, it could be a vector that only affects one direction, but it will still be a vector. And t, well, t is time, and time can't happen in 2 dimensions. So t is going to have to be a scalar. Okay. Now, the majority of our SUVAT equations will work exactly as they did before. Okay, we'll just need to think about some of the vector arithmetic there. However, some, or at least one of them, will not work. Okay. Now, squaring a scalar, that's fine. We can do that because we know we can just square a number, but we cannot square a vector. Okay, so that means that we can't use the v squared equals u squared plus 2as one. We can't use that equation anymore. Okay, so what we're going to do now is we're going to get straight into looking at a vector example involving SUVAT, and then we're going to give ourselves some time to have a look at some problems as well. Right, so here we are. First main problem. We have a particle P, has a velocity written in ij notation. The particle moves with a constant acceleration. We want to find the speed of the particle and the bearing on which it is travelling at a time t equals 3. Okay, so as with any SUVAT problem, we want to first figure out what it is we've actually got. Okay, now in terms of this, it was not going to be SUVAT, more like RUVAT. It's like Scooby-Doo has suddenly taken over doing maths. Now, we do not have position vectors. We do have a velocity. Okay, we have a starting velocity, which is negative 3I plus j. We have not got a final velocity. We're going to want to work that out. We do have constant acceleration, which is 2I plus 3j meters per second squared. We want to find the speed of the particle and the bearing it's travelling after t equals 3. Right, so we've got everything that we want, and we've got everything in the question there. We now need to figure out which equation we need to use. We want v, we've got u, a, and t. Well, that's a nice one. v equals u plus a t. So now, vectors rather than scalars. V is just going to be split up into vi and vj. U is negative 3, 1 in this case, plus acceleration is 2, 3, times time, which is 3. Now, I can do a vector times a scalar. We just times each of the numbers, and we can add two vectors afterwards. So we're going to get negative 3, 1, plus 2 times 3 is 6, 3 times 3 is 9, negative 3, 1, plus 6, 9. Negative 3 add 6 is going to get me to positive 3. 1 plus 9 equals 10. Okay. Now, what does this mean? This means that after it's had 3 seconds of acceleration, our particle is going to be moving 3 steps across. Is going to be traveling 3 steps across and 10 steps up every second. Okay, so v equals that meters per second. Okay, so that is essentially part A of this problem. Okay, but what we've got here is only a velocity, not a speed. Okay, and this is where some of the vector work that you will have done previously will come into place. We've got our velocity, but we need our speed, and speed is a scalar of velocity. So we need to find out the magnitude, the size of this vector simply by using Pythagoras. So speed will then be equal to the square root of 3 squared plus 10 squared. Okay? Which is as we've got on screen. Now for the second part, we want to find the bearing on which it is travelling. This is again some of the stuff that you would have done with thinking about vectors, but just using a slightly different context perhaps. This is travelling 3 steps across and 10 steps up for every second that goes past. Okay, so to find the bearing that it's going on, if you imagine a point and it's going 3 steps across, 10 steps up. Okay, so 10 steps up, 3 steps across. Okay, remember that bearings come from north going around. We've essentially got ourselves a nice little trig problem here to work this out. Okay, we've got to make sure that we put things in the right place. And then we're trying to find this angle here. Okay. And as I've just put up on screen, we've got our opposite, we've got our adjacent, which is why we can use tan. And then tan, inverse tan of 3/10 will give us our angle, 16.7. Okay? And remember that bearings must be written in 3 figures. It's a thing from GCSE maths, but we still need to make sure that we follow that properly. Okay? So, that's a very kind of standard thing to do. You've got your information in the question, just like we would have had with normal 2D Suvat equations. We've got the use of the equation, the working things out, making sure we read the question to take in all of the information at the very end, and then use of our trigonometry to give us the angle of travel as well as the speed. Okay. So I'm just going to quickly grab a drink. I was not prepared, and I'll be back in 1 minute. Got to stay hydrated. Okay. So, hopefully you're all still with me. Hopefully we've been able to follow that relatively well. As always, if you do want me to re-go over something, do say so. Don't just kind of let it slide by. Otherwise, we will look to move on. Okay, so we have a further example here, which kind of asks a little bit more of what you're going to find, but you'll find that the information that's contained in the question is very, very similar in terms of the setup compared to what we had before. Okay, so ice skater is on a large flat ice rink. At time t equals 0. The skater is at a fixed point O. Okay, so we're saying that at a t is equal to 0, we're at an origin point, we're at a starting point, and travels with a velocity given here. At a time 20 seconds, the skater is traveling with a final velocity here. Relative to the origin point, the skater has a position vector s at a time t seconds. So this is slightly different here. Modelling the ice skater as a particle with constant acceleration, find the acceleration of the skater, an expression for s in terms of t, the time at which the skater is directly northeast of the origin point, to start off with. Okay. So let's start off by approaching this in the same way that we approached the other one. Write out what we've got, what it is we need, and go from there. So we have our UVAT. We have an initial velocity, which is 2.4i negative 0.6j. We have t equals 20. We have final velocity negative 5.6i plus 3.4j. We want acceleration, and we also want an expression for s in terms of t. Okay. So acceleration, we've got v, you've got u, we've got t. We can use v equals u plus at and just rearrange it. That seems pretty decent. So v equals u plus at, which would then become a equals v minus u over t. We've got some substitution to do. Okay. So that would be part A. Part B, an expression for s in terms of t. So this was the first bit, which was slightly different. Okay. S is just a position vector. Okay, that's taking the pace of our r. I want to find an equation that would link either u, v, a, and t. So I've got my choice of all of these because I will have worked out my a from part 1. To give me an equation which says that s equals something. Now, if we think about our SUVAT equations from normal before we'd started doing all the vector stuff, we had v equals u plus at, which doesn't involve position at all. We had v squared minus u squared equals 2as, but we're not allowed to square vectors, so we can't use that one. We had s equals ut plus half at squared. Now, position vector we can write as s. We had ut plus half at squared. Now, we are allowed to square time, that's fine. So that could give us an expression for s in terms of t. Okay. We already have a position, sorry, not a position. We also already have a vector for u. So that could just become 2.4 times t, take away 0.6 t, like that. Half of a t squared. Well, when we've worked out what a is, we can then substitute that into this to get an expression for the other bit. So then we can have a complete thing going on here. Okay, so we can kind of put these two things together. Okay, so let's reveal those A and B. You can see how we've done using v equals u plus at to rearrange to give us something to get A. Okay, and then we've used that in part B underneath to give us this equation here in terms of t to have our position. So C is the next part, the time at which the skater is directly northeast of O. Now, if it's going to be northeast of O, east is this way. So directly northeast, that means that we're going to have an angle of 45 degrees on both sides. Okay, so you might want to have a think about now, what would we have to get to have this have an angle of 45 degrees? What would we need? Oh, no, you can leave your answers in I's and J's. I prefer using vector form. That's why I've written most of these things in vectors. But using I's and J's is perfectly fine, and you're allowed to. I don't think it says you leave it in any particular form. I think you can put it in what form that you prefer. I mean, they started in I's and J's, but they are equivalent forms, so it shouldn't matter so much what way you leave your answers, so long as you leave the right bits in the right places. No problem. Okay. So, going back to our part C, if we have that we've got 45 degrees on both sides to get from something which is directly northeast, that means that the I part and the J part are going to have to be the same to make this be almost like perfectly square. So what we're looking for is for the words. We're looking for the I component of our position to be the same as the J component of our position. That's what I want to say, right? So we have an expression by making these two parts equal. And when we've made those two parts equal, we can rearrange to get an equation which equals 0, solve some quadratics, and then we get our two solutions. Okay. Okay. So last little bit for this, and then I'm going to give you one to have a look at for yourself. We've got a second skater which travels that she has a position vector r, which is 1.1 t take away 6 j meters relative to O at a time t. So they're talking about the same origin point, and that's important with vectors. Okay, they are talking about the same origin point. We want to show that the two skaters will meet. Okay, well, if they'll meet, that means that the position vectors will be equal at a particular point, and then we will want to find out what the value t is from that. Okay, so if I show here, if they meet, the two position vectors will be the same. And this is where we do need to be really, really careful about our position vectors. The position vector here has only got a component for j. The j component is in a bracket, not to be confused with the component. I can't keep forgetting that you can't see my mouse. You can see my mouse. Can you see my mouse? I think you can. Oh. Yes, you can. Okay. So yeah, whereas this vector here is only a j component, this whole thing here has i's and j's. So the way that we can write that in column notation is that the I part of the second position vector is going to be just 0. There is no I component. So the top part of this will just be equal to 0. The bottom part of our first skater will be equal to the j part of the second skater. Okay. Now, we use this to just solve some equations again. Our calculators are great at solving quadratics, but we could solve these by factorizing, seeing as they're just t squareds and t's. So then we get two answers. We get t equals 0 and we get t equals 12. Now, we need to check some things out. We need to check that if we use a particular value of t, that both of the things work. Okay, this is something that we do a lot in further maths as well, checking that values of t work for both components of a vector. So when t equals 0, it obviously works for the top one, because that's how we got the value t equals 0. But when we substitute it into the bottom one, we would get 1.1 times 0 take away 6, which isn't the same as this on the other side, because that will just be equal to 0. So what we then have to do is we need to just double check that if we substitute t equals 12, the other value of t that we got, into these components, that we get something which is equal. Okay, which fortunately for us we do. But it is something that we need to bear in mind. We can't just kind of get to the point where we have t equals 0, t equals 12, and then go, done. We do have to check that the answers that we get work with both components. Okay. So, let me think. Is there anything else that we'll need to say from this? I think so. Anyone got any questions, or we good? I'm not prepared for this. My throat is dry. Okay. Right. So I think what we'll do then is we'll stick up the kind of final question, which will be 10 minutes for you to try and puzzle things out for yourselves. Okay. And then we will kind of go from there. Okay. So, we've got a ship which is moving with a constant velocity, and we've got at a time t equals 0, a position vector of s is this thing. Okay, so we've got a starting position. So we want to find the position vector of s at a time t. And then later on, we've got a ship t moving with a different constant velocity at a time t equals 0, the position vector is 6i plus j, and two ships meet at a point P. We want to find the value of n and find a distance of O to P. Okay. So, I'm going to give you some time to have a think about these questions up on here. And if you... At about halfway through, I'll start dropping some hints just in case people are not sure with what to do. But let's see if we can take the information that we've looked at so far and have a whirl at this. Okay. One thing I will say straight off the bat is you do have your Suvat equations, but remember as well that you also have that speed equals distance over time, or the vector version that we saw before, which is position equals velocity times by time. Okay, so some things that we should be thinking of if we're not so sure about what we're doing. The first part, we should be thinking that position is a matter of velocity times by time, but you may have to take into account any starting position that you've already got. Okay, I'm going to come back to this slide in a second, but I just want to refer back to something that we had right at the start, okay, which is this thing down here. Okay, so the position of a particle or whatever is going to be our original position vector plus velocity times by time. If that original position vector is 0, that's where we get the kind of simplified thing from earlier. Okay. When two things meet at a particular point, that means that the position vectors of both of those things will have to be the same. They will have to be equal. Okay. And finding a distance normally involves using Pythagoras. Okay. So we've got just under 5 minutes left for you to try these things out. We'll go through some answers and then we'll call that a day. Feel free to pop any questions if you've got any in chat, or if you're happy waiting on. I do highly recommend you trying some of these things out, even if you end up getting them wrong. Trying them out is the first step to success, as corny as that is. Okay. Right, so the first one we're thinking going for position, velocity times time, adding in any extra position that we've got. And the second one is thinking about solving equations using our vectors. Okay, so here's the distribution of marks. So any use of that equation that we saw right at the beginning of today will get you 1 mark. Substituting things in will get you your 2nd mark. In column notation, right, let's move those out of the way. In column notation, we just should have -4 plus 3t and 2 plus 3t. Okay. For part B, we have the position vector for the second one here. We then have the there we have it kind of all grouped together. And then when the position vectors are identical, we have that the I components will be equal. Those are the ones that they've chosen to put equal to one another. And then solving that to get our value of t, and then using that to get a value for n, which we've got there to be 3.5. Okay. Once we've done that, we just need to find out the distance from O to P, this position where they are both at the same point. Now, we can use either of the two position vectors for that, but we can we'll use the top one, I guess, just to make things nice and easy. We use our value of t, which from part B will have been equal to 2 from here. Just as a reminder, they get this stuff here from making the I components of the two position vectors equal to one another. And substitute in a value of t to get our i's and j's, and then using Pythagoras on those i's and j's give us our distance from the origin point to the point that we're talking about, the point where the two things are equal. Okay, and there we go. That's the first part of Further Kinematics. That is thinking about suvat in vector form. You can now go ahead and go through exercise 8A from the textbooks, which I believe we still have access to online. And yeah, and go for it from there. Go nuts, as I say. No problem. So yeah, I'll be sending out each week for as long as we've got things left to cover at the start of each week, what the schedule is going to be. So we've got 2 other streams going on this week. We've got one tomorrow at 2:15 and one on Thursday at 11:15. Cool. Hope that's all made sense. It looks like it's going to be a really nice day out where I am. So I hope you have a lovely day as well. And yeah, don't let lockdown get you down. Find something interesting to do, even that if is practice maths. No problem. I shall see you all tomorrow afternoon. Bye.